Have you ever considered what causes gravity? My name is Francois Zinseling, and today I will attempt to explain that to you. That will be the easy part because I will let the mathematics do the explaining for me. The difficult part will be to introduce you to the omnidirectional photon flux. This has been attempted by many before who have failed. Consider some of the known properties of light. At this moment, light is reflected in this room off my face and captured by this camera. X-rays, however, work slightly different. X-rays, also part of the electromagnetic spectrum, are much higher frequencies than visible light, and they have the ability to penetrate some matter, for instance, a human body. In the case of X-rays, though, the image that is created from the X-ray is not from the reflected light, but from the light that traveled through, for instance, the human body. In other words, it is showing an image of the light that was not absorbed. It is said that in every second, 6 billion neutrinos travel through the nail of my thumb. Yet I don't know they're there. To detect a neutrino takes very sophisticated equipment. I cannot just say, well, there goes a neutrino. What I'm trying to do here is not to imply that neutrinos are photons, although they are very photon-like. I'm also not trying to imply that the flux that I'm about to introduce to you are neutrinos, because no, they're not. But the analogy is there that the neutrinos are very difficult to detect, and so will be the flux. We will not ultimately find the flux as in there goes a flux, but we will find the flux in the effects that it has. Another property that we know of light photons is that they have the ability to transfer momentum. In the case where a photon is absorbed, all the momentum is transferred onto the surface or the object where it is absorbed. If, however, the photon is able to travel through the object, as in, for instance, a photon traveling through glass, the momentum is only transferred while the photon is in transit. Consider, for instance, this glass object. Let's say this pen is a beam of light. When the beam first enters the glass, momentum starts being transferred at this point here. On a macroscopic level, we say the whole glass is moved, but on a quantum level, this part of the glass cannot move before the photon gets there. That is just not allowed. The beam enters the glass and starts to transfer momentum. Once the entire beam is in the glass, the maximum momentum is transferred onto the glass at that point. Then, as the beam starts to exit the glass, the photons regain their initial momentum and go on their way. In that short space of time, this piece of glass has moved. We have now considered two properties of light. One, in the case of X-rays, we have shown that light has the ability to travel through some matter. I would like to introduce the flux to you as photon-like of such magnitude of frequency that it has the ability to travel through all matter, mostly undetected. Secondly, we have shown that photons have the ability to transfer momentum. Even if they travel through matter, momentum is still transferred. Both of these properties are essential in our consideration of the omnidirectional photon flux. On screen now is a 2D representation of flux traveling through a mass. Equal flux from all directions will not disturb the mass. What goes in one side goes out the other side. If the flux from the left equals the flux from the right, the mass will not know the flux is there. It will not be disturbed. It will not be moved. In other words, in a balanced flux, a mass is not disturbed. On screen is a system with flux in balance from top and bottom. There is no net disturbance on the system, which includes the hand and the Earth-like mass. The flux is omnidirectional, meaning it's coming from all directions. We represent it here on the page in 2 dimensions. And what we do is we take all the photons from the left-hand side of the mass and we sum it up to one photon of magnitude E0. We take all the photons from the right-hand side of the mass and we sum it up to a photon of equal magnitude E0, but in opposite direction to the other photon. Because the mass is stable in a balanced flux, the two photons are obviously equal. shown here with the two equal photons, the mass is still in balance. Here's why I do this one-dimensional summation. If I want to move any mass, and I'm not including rotating a mass, if I want to move this anywhere, I have to choose a direction. In any finite time dt, I can only move this object in one direction, whether it's towards you, towards me, this way or that way. I have to choose one direction in the entire 3D spectrum in which to move this object. We have chosen the x direction in which we are going to accelerate our mass. We show here that the mass is stable in a balanced flux. Flux equal from the left-hand side equals flux from the right-hand side. In other words, the mass is not disturbed. What is really happening is that in the totality in the 3D image, all the flux from the left enters the mass, transits the mass, and exits the mass in equal magnitude as from the right-hand side. We are now going to apply a force to this mass for a fraction of time dt. In that instance, we will accelerate it to a velocity gamma dv to comply with special relativity. The photons that were inside the mass at the moment of the force being applied are necessarily transformed. They exit as shown here as E1 and E2, E1 with increased magnitude of energy and E2 with decreased magnitude of energy. This is in accordance with the Doppler principle, of which the equations are shown here on the screen as well. When we further analyze the photons E1 and E2, if we look at the mods of the energies of E1 and E2, the change in energy that happened on the right-hand side, E1 minus E0 is the change on the right-hand side, E2 minus E0 is the change on the left-hand side. When we take the total change of energy of the photons, and we set that equal to the change of energy of the mass, which means the energy of the mass is changed via kinetic energy, we find that this relationship emerges. Keep in mind that when Einstein did his equation, when Einstein acquired his equation E equals mc squared, his outset was E over 2 for each photon. Further analysis of the photons E1 and E2. If we look at the difference of E1 and E2, we take that energy value and look at the momentum component of that. We set that equal to the momentum that has now been gained by the mass. We end up with the same relation, 2E0 equals mc squared. Furthermore, if we look at the total energy of E1 plus E2, we get the total of the energy of the kinetic energy of the mass plus mc squared. What we have done here is we have shown that from the energies of the photons that were transformed when we accelerated the mass, we are able to derive equations of motions. We have not only shown here that mass is a function of the flux, but we have also shown that the energy of the flux determines the mass of an object. We have now accelerated our mass to a velocity dv, to be specific gamma dv. While this mass is now in motion with a velocity dv, flux is still entering and exiting from both sides in the x direction as we have started off. Because there is no force being applied, the flux is not being disturbed. Therefore, the flux must enter with E0 and it must exit with E0. From both sides, the magnitudes will still be in balance. This will allow the mass to continue in motion without being slowed down, and is also in accordance with Newton's first law. The original photons, after we accelerated the mass, exited with magnitude E1 and E2. Let's say we could capture those photons, turn them around, and point them back at the mass. We would necessarily take all the energy and momentum that was given to those photons and transfer it back into the mass, which must then put the mass back to zero. What we have done is we've reversed the initial force that was applied to the mass, and we have now brought it back to a velocity of 0 by using photons. If we are able to supply a constant stream of photons E1 and E2, where E1 and E2 are not equal magnitude photons, we now have a mass in an imbalanced flux, which will result in the mass being accelerated. Consider the neutrino analogy we had before. On the right-hand side, we show a system now which is no longer in balance. If we can show that somehow the Earth absorbs some of the flux, then a lower magnitude of flux will exit the Earth between the Earth and the hand, and that will result in a net force on the hand pushing the hand downwards. Until this point, we have taken it that for any mass, flux in equals flux out. This was done to set the scene up until this point. To attain the mechanics of gravity, however, we have to assume that a small portion of flux is absorbed in any mass. This will follow from the equations in the paper and is necessary for the mechanics of gravity. We can also safely say that during the absorption of flux, if we take a scenario of 100 flux go into a mass, we would say that 100 flux come out, and those that interacted with the mass would come out with slightly less energy on each of them. We would not assume that flux is wholly absorbed. And the reason we can safely say that is we know that an X-ray photon absorbed in a human body has the potential to cause great harm. If a flux photon is thus absorbed in a body, it would cause even greater harm because we take it as of being a higher frequency and thus a higher energy. Since the flux is not destroying me as I'm sitting here, I am experiencing the effects of flux absorption and the effects of gravity. We now have the mechanics necessary to describe how the omnidirectional flux can enact gravity through a push force. By a small absorption into one mass, in this case, let's say the Earth, the flux in from the bottom would come out reduced at the top. This would leave a net effect of a inflowing flux from the top, which would push, for instance, the body of a person down onto the Earth. Of course, the same applies in the other direction where the person is also attracting the mass. This we will show in later slides. Consider some history, because push gravity is not a new thing. In 1687, Newton published his Principia, which we now know as his Newton's laws of gravity. It wasn't long after that, in 1690, that Fatio proposed to Newton that the mechanics of gravity had to be as a result of a push force. Newton briefly considered this, but ultimately rejected it, and subsequently had a fallout with Fatio. Fatio remained unpublished. In 1748, Lesage published a paper based on Fatio's ideas, now called Lesage's push gravity. It was met even then with resistance, and any attempt to revive the theory has been met with vehement resistance by the likes of Maxwell, Laplace, and even by the great Feynman himself. At the moment, our best theory of gravity is contained within Einstein's theory of general relativity. The gravitational constant G features in any equation of gravity that you might encounter. On the screen, we have two representation of two of our main theories, being Newton's and Einstein. In the case of Newton's theory, we understand that to be a pulling force between two masses. This is relative to the value of the two masses, and also relative to the inverse of the square of the distance between them. The net answer we get, though, is that there is a pulling force between two masses. How that pulling force arises or what causes it, we do not know. In Einstein's case, there is a slightly better way towards describing gravity, in that it tells us that mass bends space, and that space tells mass how to move. So in other words, if we have bent space, mass will not move what we consider in a straight line. It does not clearly tell us yet, though, what space is or how mass tends to move space. Consider the units of G as Newton meters square per kilogram square, as shown on screen. Using G in Newton's equation returns a unit of force, which shows us the magnitude of attraction between two gravitational masses. Let's rewrite those units as shown here. Same units, just written in a different way. Units of G shown as meters square per kilogram times Newton per kilogram, where meters square per kilogram is typically used as a coefficient of absorption. Newton per kilogram is more self-explanatory in that it tells there is a force per mass. This will be our coupling constant, and we will need both of these to explain the interaction of the flux with mass. Consider the gravitational interaction between two masses. With the flux theory, we are proposing that the gravitational interaction is a result of a net push force on each mass. Right now, this might be difficult to grasp, but consider standing in a strong wind. The wind is pushing you in a certain direction. Now imagine the flux as that wind, except the wind is not just pushing against the surface of your skin or your clothes. It is pushing on every atom of your body. If there's a slight imbalance in the flux, that imbalance will push you in a certain direction. Compare that to what we know gravity as a pulling force. How would that push force be distinguished from a pull force that is pulling on every atom in your body? You will not be able to distinguish the difference between the two. On screen is a typical X-ray absorption curve. The actual absorption is calculated by subtracting the exit flux from the incident flux. This curve does not just apply to X-rays, though. It applies to anything electromagnetic where you have interactions with matter. It would apply, for instance, if you're trying to send a radio signal through a thick wall or through a large, long distance of air. It would also apply if you're trying to send photons through glass. The on-screen equations will not be discussed in detail in this video. It can be analyzed in detail in the paper or will possibly be discussed in later videos. What we can take away from this page at the bottom of the page is that for any mass, the absorbed flux equals mu times flux in times the value of the mass, where mu would be the specific absorption coefficient for the mass or the type of material, as we have defined earlier when we split the gravitational constant G into two parts. The strength of the absorption would also be defined by the strength of the flux that the mass finds itself in. And the mass m, being in kilogram, is the result of volume times density, and thus applies to any shape or size of mass. We have shown that the absorption of flux into a mass is proportional to the magnitude of the mass. The value of mu times the strength of the flux is considered a part of the gravitational constant G, as we have shown earlier. Yet that alone is not enough to enact gravity. We now have a single mass that has created an absorption effect around itself, where we have flux going in and out still in all directions. Flux is omnidirectional. It comes in and it goes out. Yet, due to absorption, the amount going out is slightly less than the amount going in. This creates a net, could we call, inflow of flux into the mass. It doesn't mean it's not flowing out. It's still flowing out. It's just flowing out less. This imbalance in the flux is established around the mass big M at the speed of light. It's maintained at the speed of light, and it is re-established should the mass m be moving at any velocity v. Should any other mass, in this case small m, find itself within the light cone of big M, it will experience that imbalance that was established around the mass big M. Now, of course, the same imbalance would be created around small m, but on screen is shown only the one effect. The mass small m finds itself in an imbalance in flux, and as we have shown earlier, an imbalance in flux will cause a mass to move. Here we invoke the other portion of the split that we invoked on the gravitational constant g, where we split it into an absorption coefficient and a coupling coefficient. This will determine the strength of the push of the mass, that the strength of the flux multiplied by the strength of the coupling will determine how much this push force or the strength of acceleration will be on this mass. You may recall that the units of this factor was Newton per kilogram. In other words, there's now a force enacted, newtons per every kilogram of mass on the mass small m. And of course, the same applies in the reverse direction. The result of the mathematical equations by assuming absorption into mass and a flux coupling with mass leaves us with the resultant equation that looks like this. This may seem like a huge shortcut, but please have a look at the paper which shows everything step by step. Comparing this to Newton's equation, we see that the equations look remarkably similar except for the value of g. Here, by the assumption of flux, we have derived Newton's equation. However, what we have shown now is that g cannot be considered a constant. It must be a measure of flux, first of all, a measure of absorption into one mass, and a measure of coupling with another mass. In summary, it must be assumed that g is not a constant, and we can thus also assume from Newton's equations that Newton's equation is a simplification for interactions between two masses. One of the major drawbacks of the Lesage theory was the amount of energy calculated to be absorbed during their gravitational interaction. The amount of energy was of such a magnitude that it would typically blow up the Earth in an instant. Here we have shown that absorption and coupling have been separated, in that only a small amount of absorption is required as long as the coupling still exists. Mass still appears transparent to the flux, so if only a small imbalance in flux can be created, the transfer of momentum can still continue without any absorption. As an exercise, purely as a crude exercise, not to overthrow any known scientific theories, I've taken the outflow of heat from the Jovian planets as being all the heat generated by the absorption of flux. This is not according to known science and standard science, but is merely to try and represent what may be a quantity of absorption and what would a value of mu be if we made that assumption. For the planets Earth, Jupiter, Saturn, and Neptune, based on their masses and the measured outflows, a value of mu is calculated based on the energy equation that is derived in the paper. The values of mu are remarkably similar. No, not sigma 5, only remarkably similar. This has been, after all, a crude assumption. What it does show, though, is that the Earth does not need to blow up with the flux absorption theory. It is time to conclude and summarize this very brief introduction on the mechanics of gravity, or shall I say the introduction to the omnidirectional flux, which is a bit tougher to behold. So far we have shown from the assumption of an omnidirectional flux how inertial mass arises and how an imbalance in flux can cause gravity. We have shown through the use of a Gaussian sphere that the force of gravity dissipates to the measure of 1 over r squared, as was originally shown in Newton's equation. This, of course, applies for a single mass, and unfortunately this opposes what is proposed by the modified Newtonian dynamics. We have shown how instant action at a distance is possible, because when two masses interact, the imbalance in gravity between them is already there, having been set out at the speed of light previously. Newton's first law is upheld because a particle in motion will remain in motion unless disturbed, which is now also explained by the flux. We have touched briefly on aspects of special and general relativity. In summary, for special relativity, your relative motion to the flux is your reference frame. And in general relativity, we can say that the gradient of flux is the curvature of space. In other words, a gravitational field around a mass creates a gradient in flux. Very large variations or very quick variations in a relativistic manner will cause fluctuations in the gradients of flux, which we now know as gravitational waves. When we do look at relativistic effects, we will find that gravity does not comply with Newton's third law. In other words, the force on one mass will not equal the force on another mass. For those tasked with the measurements of the gravitational constant g, the predictions that already arise from this document is that measurements with different materials of mass, or even different sizes of mass, and thirdly, a different placement in the local flux will cause variations in the measurements of g. However slight, those variations will be there. Anyone who has worked in field theories, whether be it electromagnetism or quantum physics, may already see the benefits of this omnidirectional flux, the applications thereof. Quantum physicists already know that the energy of space is much, much more than we can imagine. I do believe that with the application of the omnidirectional flux, we are moments away of having a true quantum gravity theory. One last item I would like to leave you with to think about, and that is the dark matter. On screen you see a crude representation of a galactic disk viewed side on, where the view of the plane of the disk presents us with a line of material. Applying the same principles as we have done thus far to the mechanics of gravity, we have, let's say, this galaxy in a relatively balanced flux. In other words, from the left and right into the plane, the strength of flux is more or less equal. As we see the flux enter one mass after another, due to the absorption of flux, the strength of the flux is reduced. This changes the local flux at each point as it progresses, and of course, due to the mechanics of the equation, must change the gravity at those points. However, what is to note is that when the flux exits on the other side of the disk, it has been greatly diminished, meaning that the masses on the outside of the galaxy do not find themselves in a balanced flux. They do find themselves, in fact, in a very imbalanced flux with a very large push component towards the inner side of the galaxy, and therefore higher relative orbital velocities. This may not be an instant answer to the problem of dark matter, but it may assist us towards finding the solution. I thank you.